We're starting a new topic. We are leaving the wonderful world of energy.
I would love to go back to it as if we don't have to do this.
Actually, you know what? Most of you will... Energy should be one of the tools in your physics toolkit that is your favorite. Okay? Because the nice thing about energy is that once you kind of understand how energy behaves, or at least how it works, then you don't need a lot of math, right? It's pretty straightforward. There's no trig involved, really. I mean, there's cosine, theta when you do work, but other than that, I mean, it's all just regular algebra, real straightforward, okay? We're jumping from that world of numbers called scalars. Scalars are numbers that don't have direction, okay? Like money doesn't have a direction. Time doesn't have a direction.
Forward.
Time does not have a physical direction, okay? Mass does not have a direction. All these things are scalars. Kinetic energy does not have direction, nor does potential energy, okay? Kinetic energy doesn't have direction because if you go one way or the other, it's still positive, right? There's no positive or negative to show you the directionality of it, right? There's no vector associated with it, or an arrow, okay? We're getting into the realm now of vectors and how you handle vectors, okay? However, if you can solve a problem with energy, please do. Because if you can solve a problem with energy, it's almost always the easiest way to solve the problem, okay? It's the least complicated math way to solve it, all right? So even when we go through kinematics, think about it in terms of energy as well. You can solve some of the kinematic stuff that we're going to go through, trajectory motion and all that stuff, with energy, but not all of it. The problem with energy is that energy, because it's simple, the math is simple, it doesn't give you as much information. If you want more information, you have to go to a more difficult kind of math, which is trig and geometry, okay? That doesn't mean that it's going to be undoable. It just means that there's going to be a little bit more math involved in these problems that we're going to start, okay? So don't let them psych you out. But we have several things that are vector related. That will be kinematics, like displacement, velocity, acceleration, forces, momentum. That's small p, momentum. Okay, all these are vectors. And in your textbook, they'll be capital usually, or italicized. I'm sorry, or bolded, I mean. Since we can't bold them on the board, we usually write them with an arrow over the top telling you that it is a vector. On the other hand, we have a lot of scalars. Scalars are mass, time, kinetic energy, potential energy, heat, temperature. All those things are scalars. No directionality associated with them. Okay? There is a big difference between scalar equations and vector equations. If there's vector equations, we have to use vector math, geometry, and trig. If it's a scalar equation, we can just use regular algebra. Like for instance, PV equals nRT. Scalar, 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 scalar. So we don't have to use any trig. All right? Delta U equals Q plus W. All scalars. No vectors involved. Okay? However, when we get to things like F equals MA, okay? The stuff on the left of the equal sign has to equal the stuff on the right. The magnitude here has to equal the magnitude here, right? Same thing over here. The magnitude on this side has to equal the magnitude over here. But more than that, the direction of what goes on over here has to equal the direction of what goes on over here. So the magnitude and the direction have to be the same. Okay? So, we're going to start off with the basic vector stuff, which is kinematics, just the study of motion and how we describe motion. Now, it's important to note that we don't know, or we don't care in kinematics why or how the object got this motion. We're just wanting to understand or just describe, its motion. That's all we care about. Where is it at? How fast is it going? What's its acceleration? And at what time is it doing these things? That's it. Okay? We don't care how it got there. All right, so. Uh-oh, too late. It was displacement, velocity, acceleration, forces, momentum, I think. F and small p. All right? Okay. First of all, let's make sure we have a couple of definitions down right. We know what a vector is. Vector has a magnitude and direction. You know that already. A magnitude, by the way, is a number with units. The number tells you how big, and the units tell you how big of what. So without units, we don't know what it means. So you must have units on all your answers, if there is a unit to be had. There are a few things that are unitless. Okay? Such as coefficient of friction, index of refraction. I'm trying to think of another one. Those are the two biggies that I think that we will use in class. All right? A scalar, on the other hand, a scalar is only a magnitude. So it's just a number with units. That's it. No direction. So the math here is algebra. Plus, minus, divide, times. That's it. Algebra. Up here, we're going to have to use right triangle stuff. Sine, cosine, tangent, and algebra. Okay? So up here, the vector math is a little more complicated. All right? Not that big a deal. So let's make sure we get the difference between these two. Speed is a scalar. Velocity is a vector. Okay, in your car, there is a speedometer, a speedometer. Okay, so is it a speedometer or is it a velocity-o-meter? Speedometer. Why is it not a velocity-o-meter? Because it's always positive, and it doesn't tell you direction. How would it be different if it was a velocity-o-meter?
It would go negative 10 miles per hour. You're going back.
There's a couple of ways. One is that if you went forward, it's positive. If you go backwards, it's negative. Well, it has to be a little bit more than that. You'd have to decide which way is positive, like east maybe. So if you drive towards, Shreveport, it would be positive. If you drive towards Fort Worth, it would read negative.
But
what if you go to Houston?
Wichita Falls.
Or Wichita Falls? What was your suggestion?
You'd have to have another different thing.
Yeah, or you could have it where it gave you a magnitude, like how many miles per hour, and it gave you a direction. So some cars that you've been in have a compass in it, right? So it gives you speed and direction. So that technically is a vector, right? So combined it would be a velocity-o-meter. Here's another way you could have a velocity-o-meter. You could have a dial like this that in the center means 0. And the faster you go, the arrow coming out gets longer. And if you're going south, then the arrow would be this way. Or it would turn as you went different directions. Right?
Shrinks and extends.
Yeah, shrinks and extends and rotates. That would be a way you could do it as well, right?
It could be a metal.
Yeah.
You know what you can do, Mr. Boone? It could be a metal, and then the faster you go, the more heat there is, so it extends more by thermal expansion.
There you go, thermal expansion.
Wouldn't that be dangerous? It's like,
Where am I going? Boom! Yeah, that would be confusing. Actually, just your speedometer and a compass would work fine together. All right. Well, wait a minute. So speed is always positive, right? It doesn't matter. This could be positive or negative, or it has to have an angle. So there are a couple of ways that we can describe direction. If we're talking about a one-dimensional world, like this, there's 0, that way is positive, and that way is negative. And if I say I'm traveling negative 10 meters per second, what am I doing? Am I necessarily going backwards, or am I just going that way? Okay, my orientation may be whatever, but I'm going that way at 10 meters per second, as opposed to positive 5 meters per second this way, right? Okay, but what if we're in a two-dimensional world? How do we designate direction in a two-dimensional world? Say you've got, say you got a frog is on the floor here, and that frog is jumping around, and you want to know what its velocity is, but its velocity would be how fast it's moving, but also which direction it's moving, right? So there's a couple of ways to do that as well. In two dimensions, you can either break it up into x and y components and say that the frog, if the frog, shoot, can I draw a frog?
Fail.
It hasn't jumped yet. All right, so the frog's going to jump this way. If the frog jumps that way, it'll have a velocity in the x direction and in the y direction, correct? Okay, so you'd have to have the x component and the y component. Now, you've all done this in pre-cal. So if I told you that the x velocity of the frog was positive 2 meters per second and the y velocity of the frog was negative 3 meters per second, which direction would it be going?
Wait, what? I didn't hear.
All right, I'm going to say it again. If I told you the frog was going a positive 2 meters per second and a negative 3 meters per second in the y direction, which way is the frog going?
Southeast, west.
Southeast, yeah.
Yeah, it's going to the east, or in the x direction, and in the negative y direction. So it's going to be going that way and that way, right? 2 and 3 for a grand total of, Pythagorize it, right?
4, 9, 12,
3, 9, 4, square root of 13.
13. Yeah.
Okay? Got it? Okay, we could do that. Or we could say something like, instead of doing it this way, component notation, okay, we could say something like, hey, well, the frog's going 5 meters per second at an angle of, 27 degrees. That would be another way to designate it, right?
Yes.
Right? Right?
Yeah.
This is 56 degrees here.
That's crazy.
So I could say the frog is going the square root of 13 meters per second at an angle of 56 degrees. Ooh, but wait a minute. Wait, there's more. 56 degrees
From where?
from where?
From the
North to
x-axis. From the east.
How did you measure angles in math class?
From the origin.
Like this? X, Y.
From the x-axis.
From the x-axis, which way?
Whichever.
Counterclockwise.
Yeah, that way for those of you that... Yeah, see, that's clockwise. For those of you that have only digital clocks in your house. So counterclockwise, right?
That clock's really wrong.
Yes, it is. So counterclockwise this way. Uh-oh. So wait a minute. See our angle down here? What kind of angle is that? That's way the heck down here.
Acoustic.
So it's 56 downward, negative.
Like 2 some
56 degrees
meters
clockwise. Or you
56 degrees clockwise?
From the axis.
All right, if you were in math class, then you would say this angle.
304 degrees.
How big is that angle?
304.
Big.
Over 270.
0, 90, 180,
It's this
270, plus this. Or you could say it's 360 minus 56, right?
It's an angle about this.
What? That doesn't make sense.
Okay, the angle is what? 304 degrees. Okay, that's called polar coordinates. We'll get into that more a little later. Okay. All right. Let's talk about the difference. Let's talk about the difference between distance and displacement.
That's wrong.
That's not wrong. This angle?
No, no.
I don't like your clock. It's really dirty.
It's not dirty. It's an antique.
Yeah, it's old.
It's lying to me.
Yeah, that's not the
Rudy, leave it alone. Rudy,
Well, I put it up there.
put it back.
But it's lying.
So it was in my way. It was right here, so I took it. I put it up there.
Well, that clock is giving you more physics time. You should like that clock.
Less lunchtime. I don't like that.
No, it just means that your day ends later.
Let's.
This is not good.
They give us little time, crappy ass food.
Okay.
Not very good.
No, I want to be electric. You're the one that I want.
Okay, let's talk about the difference between distance and displacement. Okay. Distance tells you how far you've traveled. Okay? Distance tells you how far you've traveled. Displacement tells you
How far you are from where you started.
the straight line distance, how far you are from where you started. Okay? So like for instance, if you're here and you walk around like this to here, the distance is all of this pathway. But the displacement is from the start to the end.
How far apart they
It's
are.
the shortest point.
It is.
The
It's
shortest
this. That's the displacement.
line.
The straight line from there. And the thing is, everybody, the displacement also is a vector. So you need to associate it with an angle, telling you which way. All right? So like, this looks like, a certain distance at 0 degrees or to the east, right? Which is different than the same distance to the north. Okay? You end up in a different place. So distance doesn't tell you where you're at. It just tells you how far you've traveled. Okay, so on your car, you have an odometer. An odometer. An odometer. Okay, is the odometer, is it a distance-o-meter or is it a displacement-o-meter? It's a distance-o-meter. How would your odometer be different if it was a displacement meter?
It would be about
It'd be 0 when you come back home.
Yeah, well, if you set it 0 at home, then when you returned home it would read 0.
Hey, somebody moved my house.
That's right, it would be easy to find your way home. Just keep driving until it reads 0. Right?
It's getting bigger. This road.
I'm going the wrong way. Turn around. Alright? That's all you have to do.
Lisa, it's not that funny. You like turning red.
They thought you're funny.
Alright.
Reflection from the sock.
So, displacement, velocity, and acceleration. Okay, everybody, you ready? Displacement tells you where you're at relative to some reference point, relative to where 0 is. So displacement tells you where you're located, like on a grid or in a reference to some location. Okay, you got that? Relative to a reference point. Velocity tells you how fast you're going and in what direction. So how fast and in what direction. Acceleration tells you
This is slow velocity.
acceleration only tells you one small thing. It tells you how your velocity is changing. That's it. You ready? Acceleration tells you how your velocity is changing, and that's it. So let's see if you get it.
remember last year Mr. Carter got mad because we said deceleration.
Yes, don't use deceleration. Occasionally it slips out because in the English language it means something, but in physics, not so much. There's really no such thing as deceleration if you use the term properly.
You just have acceleration in the opposite direction.
That's correct.
The negative direction.
All right, here you go. Here's 0. Here's my number line. I'm living in a one-dimensional world here. 0, plus, minus. Okay, if I have a displacement that's positive, a velocity that's positive, and an acceleration that's positive, tell me, what am I doing? Where am I at? I'm over here?
Yeah.
Doing what?
Going that way.
Going that way and doing how?
Getting
Getting faster and faster that way, right? So I'm starting off slow and getting faster going this way, right?
Hit the captain.
You're so fast.
Uh-oh.
Well, so you hit the captain falls.
Okay, so now the magical negative sign. What changes?
We're getting
slower.
I'm here, but I'm going that way?
Going back, slowing down.
Slowing down.
So I'm going fast, but then I'm slowing down. Stop it, dude. Serious. All right. So I'm slowing down. Okay, now wait a minute. What if we've got negative, negative, positive?
You're going
Wait a minute, where am I?
You're going that way.
I'm here.
Speeding up.
I'm going this way.
No,
No,
backwards.
it's
You're going that way.
slowing down because it's relative to the positive.
I'm going-
so it's slowing down.
I'm skipping.
Yes.
Going that way and getting
So you're
faster.
going that way, you're
What are
going
you
back.
doing?
You're slowing
Okay, first,
down.
one step at a time. Where am I?
Negative.
Here. Which way am I going?
That way.
That way. How is my velocity changing?
It's becoming positive.
Going that direction.
Okay, I'm here. My vector, my displacement vector is like this. Let me draw it on the board. So here I am. Happy Mr. Bruin. Here's my displacement vector, x, from the origin to here. My velocity vector is this way. Notice that's negative in this direction, right? But I don't put the negative because I'm showing the arrow. Okay? My velocity is in that direction. But which way is my acceleration?
Positive.
That way. Whoa, 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 whoa. So what does that mean? Am I going backwards, speeding up, slowing down? What am I doing?
Going that way, slowing
Okay,
down.
I'm going that way, but I'm accelerating that way.
You're slowing down.
Yes.
Slowing down that way.
You're slowing down relative.
I'm slowing down that.
When you're going
Yeah,
down.
you're slowing down that way.
I'm going that
speeding
way,
up
but
that
I'm
way.
slowing down.
That way.
Right?
Yes.
Yeah.
Slowing down
Okay,
that
here's
way,
the deal.
speeding up that way.
If I'm going that way, but the acceleration is this way, remember acceleration is change in velocity over change in time, right? So let's say that my velocity is originally 8 meters per second. Let's say this is 1, make it easy. But that's negative and that's positive. So after 1 second, meters per second squared, after 1 second, how much will my velocity change? 1 that way.
It would be negative.
So that means after 1 second, my velocity now is -7, right? And then I add 1 more that way after another second, right? And so now I'm 6, and then 5, and then 4, and then 3, and then 2, and then eventually 1. And then 0.
Negative.
Then you stop.
And positive.
And you start going around.
And then if the acceleration continues, what do I do?
Turn around.
I'll go like this, and I'll slow down to a stop, and then I'll turn around and start speeding up this way, right? Because what happens is I'm going this way, and my, ooh, these are smelly, low odor. That's what they say. Velocity, acceleration. So my new velocity, acceleration. New velocity, acceleration. New velocity, uh-oh, acceleration. What have I done? I've now turned around, and look what happens now. They're adding because now they're in the same direction. So what is the key for slowing down? What does that mean?
Speeding up.
If you're slowing down, no, don't say deceleration.
It's speeding up in the negative direction, the opposite of your
If you're
velocity.
slowing down, if you're going that way and slowing down, which way are you accelerating? That way.
Opposite sign, velocity versus
Okay, the
acceleration.
key thing is that to slow down means that your velocity is in one direction and your acceleration is in the opposite direction. Speeding up is your velocity is in one direction and your acceleration is in the same direction. Does that make sense?
Can you repeat
Are you?
Okay, what am I doing?
Moving.
Slowing down. What am I doing?
Speeding up.
Speeding up. What am I doing?
What am I doing?
Speeding up.
What am I doing?
Same. YMCA.
I can't spell. You're going to the Y-N-P-U.
P, what do you mean?
Well, your velocity.
No, it's an R.
Velocity is the same as the position.
Okay. The question is wouldn't your velocity, first of all, let's clear this up, make sure we get this. Does everybody see that acceleration and velocity can have opposite signs, and when they do, you're slowing down?
Yes.
Okay, does everybody see that a positive acceleration can mean slowing down,
Yes.
How much is that?
and a negative acceleration can mean speeding up?
Yes.
Everybody got that?
Yes.
So if velocity is negative and acceleration is negative, you're slowing down.
No,
If velocity is negative and acceleration is negative, you are
speeding up.
speeding up
In the negative direction.
in the negative direction.
I got it.
Okay, now the question was, do these two have to have the same sign all the time?
No.
No. So like for instance, I could be here, but moving that way,
And
Or you
accelerating.
could be there.
and accelerating that way.
Yeah.
But I could be anywhere location-wise and traveling east or west, right? It doesn't matter. Okay, we got it?
Yeah.
Excellent. All right. All right. Oh, almost dead, Mark. Okay, everybody. What's this person doing?
Positions the
Standing in the same spot.
They're breathing.
Constant
That's
acceleration.
It's bending.
Perhaps they're not
No,
breathing,
they're
they could be
staying in the
dead.
same
Zero velocity.
I agree, Lisa. They have a constant acceleration.
Zero.
Yes.
Zero. Yeah.
What is their constant acceleration?
Zero.
Zero. Very nice.
Constant velocity.
Okay, what is that person? If that was me, what would I be doing?
Stand still.
Right there.
Standing right here and not moving. Okay, how would that be different from this person?
Is that
It's
supposed to be horizontal or
Yeah, they're not here, they're
Over there.
here.
So that's also horizontal.
Or what about this person?
Oh, you way over there.
Yeah, they're way over here. That's
no, it's
Rudy.
in an opposite direction, so they're over there.
That's time out. All right.
Get it? 'Cause it's
All right. Okay. Wait. This is standing still or not moving. That means a velocity of zero. Velocity of zero. Okay. Now slope. What's the slope here?
Zero.
All right. Slope physically is rise over run. What's our unit for rise on here?
Position.
Meters.
Meters. What's our unit for run? Seconds. So our answer will be in meters per second, which is velocity. All right? All right, which is the first derivative, right? Okay. So, hey, the slope here gives us the velocity. Okay, so everybody, x, t. What is this person doing?
They're
Moving forward. No?
They start from a negative position and they're moving forward.
Okay, let's put our zero back up here, and that's positive, and that's negative. So where did I begin?
At negative.
And then what am I doing?
You're moving that way.
Moving that way at a constant rate or constant velocity, correct? Okay, so what would be the difference between that and this?
He's moving
Moving
faster.
fast.
Okay, starting at the same spot, but moving faster, right?
Constant velocity.
And another constant velocity because the slope is constant, right? So a bigger slope means a higher velocity. So big velocity here, smaller velocity here, zero velocity here, right? Sorry. Velocity versus time. Velocity versus time. Okay? What's that person doing?
Yeah.
They're standing still.
Wait, no,
We're moving
constant.
to the velocity is constant. Yeah.
Is the person standing still?
No.
They could be.
They could be.
Well, if you have
Really?
No, they're moving.
If it was zero, it'd be down here. It's positive,
Well,
constant velocity, so he has to be moving. If it were not moving, he'd be at zero. Like he'd be.
Okay, not moving here could look like this, this, or this, right?
Yes.
What does not moving on here look like?
Exactly. Like,
Zero.
just
You need to have a velocity of 0, right? Velocity of 0 is like right there, right?
Yes.
So that's not moving.
Yes.
Velocity equals 0. So what's that person doing?
Moving.
Moving. Which way?
Positive.
Positive direction.
Yes.
At a constant rate.
Yes.
So that matches
That.
that, right?
Yes.
Where this slope is the same as that number. Correct? Is that correct?
All I think about is calculus.
It's his calculus. All right, so actually calculus, one of the developers of calculus was Newton to solve these problems. Okay, now, what does speeding up look like?
What graph though?
Excellent question. Which graph? Okay, how about this graph? XT. What does speeding up look like?
Yeah.
Because speed, or velocity, is the slope, right? So you got to have a slope here, and a new slope here, and a new slope here, right? So that's a curve, right? Because the slope here, and here, and here have to be different for you to be speeding up.
And they have to be increasing.
And this is increasing, right? Excellent. Hey, now wait a minute. That's an acceleration. Is that a positive or negative acceleration? How do you know?
Because it's increasing constantly, so velocity has to be positive.
Okay, so let's do this. How about this one? That slope right there, that curve. Is that a positive or negative acceleration?
It's still positive. The acceleration is negative. Acceleration is negative because it eventually is going to stop. Velocity is going to go to zero. Or at least we think.
Hey, here we go. Shh. Here's the original velocity. What kind of velocity is that? That's a negative. It's a big negative velocity. What's the velocity like here? Smaller negative. What's the velocity like here?
Zero eventually.
Okay, so wait a minute. Let's figure that out. So which way was I going? That way fast, right?
You're slowing down now.
And I'm slowing down while I'm going that way. So which way is my acceleration?
The other way is positive.
That's a positive acceleration. Now from calculus, that means anything concave up is positive acceleration, right? So if it's concave down,
It's negative.
it's going to be negative acceleration. That's a little bit harder to understand. Almost everybody gets this one right, but this one right here is pretty challenging. Okay, it's harder to think about. Okay, so here we go. Let's make sure we get the connections between all these. Acceleration versus time, velocity versus time, displacement or position versus time.
Okay, the derivative of time.
And even if we're doing a lab and time is not our independent variable, we will still graph it this way using poor scientific technique, because when we graph it this way, then the slope of this graph is velocity, and the slope of this graph is acceleration. That's why we do it this way. It's a standard way to graph these. Okay? So, what's that?
Constant acceleration. Constant positive acceleration.
Okay, if I have a constant positive acceleration, what's this graph going to look like?
It's going to be increasing. Slope is positive.
Because the slope of this graph equals acceleration, right? Because this is meters per second, and this is seconds, so meters per second per second. That's what acceleration is meters per second change every second, or meters per second squared. There's no such thing as a square second. It's really meters per second changing every second. So like the acceleration due to gravity, it's about 10 that way. That means if you fall off a building and you fall for a second, your speed will pick up that way, 10 meters per second, every second. So if you fall 10 seconds, you'll be going 100 miles an hour. Sorry, 100 meters per second. If there's no air resistance, right?
But there is.
But there is, so you won't quite be going that fast. Believe me.
What's the fastest you can travel?
Terminal speed.
That is
All right, so this one's going to look like
this.
this, or something like this. It doesn't matter, does it? You can shift up and down,
C
because the slope here equals this.
plus C.
Okay, now, if this graph looks like this, what's this graph look like?
X squared.
It's going to be like this somehow or another, concave up. It could be this part of the graph or this part of the graph. Could be below here or whatever. Okay, here's the deal. If this is constant, then over here we get y equals mx plus b, a line. And over here we get y equals ax squared plus bx plus c. Our equations, on the other hand, will look a little different, though, because we don't have y and x. Ours will be v equals the slope, which is acceleration. X is time. B is, that's the initial velocity. So v equals v naught plus at. Right here. Ours looks like this. X equals x naught plus v naught t plus 1/2 at squared. Hey, shut up. Quiet. Shh, listen. X equals x naught plus v naught t plus 1/2 at squared. Unfortunately, in math class, they start with the highest power and work down, and us, for some reason, in physics, they start with the constant and move their way up. So it's like the equation swapped around.
Why don't you just swap it?
Is x distance or
That's the way you'll see it. Okay, x is the displacement. So it's quadratic. Yeah.
Yes, that's what we were just talking about. Being a water system.
Oh yeah, that's when we're doing vertical. We'll do that next time. Three-dimensional motion. Hey, the archery of doom is an extra credit problem that'll be due next week.
Alright.
It'll add points to your next test.
How many?
Points.
How many?
Points.
More than one.
Points. It's worthwhile. Points on your test, your next test. The archery of doom is extra credit. It adds points to your next test.
Trajectories.
Trajectories. You love trajectories.
That was the worst part of
You can